suppose we are given a sequence over natural numbers, and we ask the question: does this sequence correspond to a probability distribution? Does this sequence correspond to the moments of a probability distribution? In other words, is there a probability distribution on reals for which Q0, Q1 is the first moment expectation, Q2 is the second moment, and so on? So, and Hamburger, I guess, Hamburger showed that basically, if we such a function is a moment, such a function is a legitimate moment function if and only if the corresponding matrix if and only if the corresponding matrix is positive definite. So basically, we at ith, jth column of this matrix, we have the entry I plus j. And basically, in order to test whether a given sequence is a moment function, we can just construct this matrix, which is infinitely large, unfortunately, and then check for its positive semi-definiteness. But then this can also be generalized when we have a multivariate distribution. Basically, if now instead we are given we are given the moments of k variables, we can ask the question whether if this sequence now forms a moment, this sequence is a moment distribution. And then the answer is similar again. We construct the exact same matrix where inj are now vectors over, inj are vectors of k dimensions, and I plus j corresponds to the element-wise addition.
So now you're indexing matrix by tuples.
Yes.
Yeah, exactly.
I'm sorry?
Okay.
Yeah. And but of course, all of these result in infinitely large matrices. But what if we know that the moment is what if we know the probability distribution is on, say, hypercube? So basically, suppose we are and in this case, what we since we are now looking at basically the ideal generated by the variety on variety of the corners of hypercube, we basically substitute the following relation. Basically, for example, if we were only looking at the 0, 1, if we restrict ourselves to the probability distributions on the hypercube, then what we know is the ith moment should be equal to basically the moment of the vector, which is 1 in the non-zero coordinates of I and 0 on the 0 coordinates. Basically, this corresponds to the following. So if we had x I
monomial defined by the binary vector I.
Yes. Yeah. But since the expectation is basically hidden implicit here, right? So so we are looking at this expectation, but then since this is like xi's only take values between either 0 or 1, we can instead replace all the positive powers of xi with just xi itself.
Right, so it's like imposing the relation xi squared.
Yeah. Yeah, as Avi pointed out. So then what this means is we can restrict our attention only to since any power that involves second or higher powers of a term, any I which has like a component larger than or equal to 2 is not necessary anymore. We can just look at the 2 to the n by 2 to the n matrix. 2 to the k, yeah. Where now rows and columns are indexed by subsets. And here now I'm indexing, we can index the moment function by the subsets also. Yeah. Now this gives us basically a convex relaxation for the problem of determining whether corresponding probability distribution exists or not. And this means now basically we can rewrite combinatorial optimization problems by basically polynomial optimization problems involving the hypercube.
So just to make sure I understand, so now we insist that every random variable gets only 0, 1 values.
Yeah, so basically we have like probabilities on each corner of the hypercube, and we are wondering whether whether there is such a probability distribution which corresponds to the given moments.
Distribution on binary vectors of k.
And what if it's vectors over a bigger alphabet?
Then you can
you will have
so it's not xi squared equals 1.
but also you can like also do it in actually you can also do it in another way, right? If the alphabet is finite, then basically you can have one indicator variable for each variable, which is like which is the basically you can just consider the indicator vectors of like a variable for its labeling 0, 0, 1, 0, 0, which means it has value 3. Let's say it received the third label, right? And then basically you can just substitute it. And that, in that way, you can just transform the problem as a binary, again, like the...
it's not important that the products of different values are different.
Yeah, but basically, I mean, so you can, like, again, write such a matrix, and then use, have to substitute, but then you have to substitute wherever, like, there is a in entry where, like, suppose variable u receives label I, and variable u receives label j, then you have to zero this out. Yeah. Yes, but it should be 0, right? It's the so because you cannot receive both I and j at the same time.
Right, but I'm talking about products of different variables.
Yeah, so wherever like these two appear as the in the subset, it
So for each pair you have
And there's no constraint on UI and VJ.
yeah, because yeah, it can be anything. Yeah.
It just says
and
it
then
says
you can recompute because now you still want to think as if they get only values 0 and 1.
Yeah.
Which changes the moments, right? Because if something gets values, say, 3 and 5, and then the product is 15.
The thing is, but then.
So I can factor it out also. Maybe I can change the moment.
Yeah, but the thing is, it doesn't affect the existence, and like I mean, it doesn't. So yeah, the moments will change, but the thing is, like existence will still be preserved. I mean, so if you basically lift the k lift the problem on like alphabet of size k to like a to the binary problem.
I think, I mean, so suppose binary.
Yes.
And compared to also variables that get only 2 values, but the 2 values are 0 and 3.
Yeah.
Then still, if you take a moment of a monomial that has k things,
Yeah.
then really they have like 3 to the k.
Uh,
And before it was always all of them were the same.
so
Numbers will look differently, right?
numbers, yeah, that's one thing. Numbers will look differently, but the thing is, here we are only interested in like basically, but also there is another thing you can do, right? Basically, suppose in the other case, if you had like a moment qi, you can rewrite this as by summing over all, like basically summing over all f. Suppose support of I was s on all such values, and then
Each one will be multiplied by different numbers.
yeah, but you can substitute it here. So basically, it's like related to these moments by a linear transformation, right? And then basically, you will be then asking like, then you will have some like linear map, and then times this moment map. Let's say m of q, and then you, a times m of q will give you the moments of moments corresponding to the unlifted version. Right? But the important thing is, as long as
It will lead for some problem with different numbers that we can compute for binary vectors. Right?
I'm sorry, can you repeat that again?
So it will lead, if I'm asking for, I insist that the support of every random variable is 0 or 3,
Yes.
or 5 or something, then it will lead to the existence will lead to a problem about the existence of binary of random variables taking value 0, 1 only.
Yeah. Oh, but now the number of
Moments will be different, right? So
yeah.
I'll be able to compute it and
Yeah, but the thing is, it has like now 3k variables, right? The binary problem. And then we have the constraint that basically in each 3 by 3 block, like it's supposed to be like diagonal. No cross entries can be 0. And then in that case, you can basically like the moment of the let's say original problem on 3 variables will be equal to the some matrix A times m of k on like 2 variables times A transpose. And
then it will lead to a question about binary things, about the cube, but
3k binary things.
yeah, because we would have this restriction.
Yes. Yeah. And yeah.
It's still, you're saying it's still positive semi-definite program.
Yeah. Yeah. Because after all, we just like multiplied on A transpose, right? So if like
have another additional relation.
yeah, but it's not needed. It's like you don't have to explicitly enforce it. Oh wait, additional relation, you mean like the consistency constraint?
Yeah, no, I understand. Yeah, because the zeros will follow from the moment. It will be some of the moments.
Yeah.
That this random variable cannot be 5 and 3 together.
Yes. Yes. So one other way to think about the entries of this matrix is basically relaxation of an indicator function, where Q of basically now Q of S corresponds to the probability that all the variables in S are ones. Yeah. So basically, if we were if there were, suppose there was a hidden distribution on 0, 1 suppose there was a hidden distribution on subsets, and then Q of S basically corresponds to the probability that S is a subset of T. Or expectation of yeah. So now this means we can model any problem which involves minimization or which involves polynomials over which involves optimization over polynomials on hypercube as follows. So if we were given if we had a problem of this form, then now we can basically express this problem using, we can express this problem as a convex, in fact, as an SDP problem in the following way. Minimize S, Fs So basically, we don't want the trivial solution of all zeros. Therefore, we enforce the upper left. We enforce that the basically the function, the constant function should evaluate to 1, and then this is the moment constraint, and then now the evaluation of the polynomial only becomes a dot product. And now this suggests, so still the problem has 2 to the n size, so 2 to the k size. But this now suggests a very simple way to basically obtain a relaxation of size n to the r. And forgive me, I need to change the set of variables with n instead of k. So basically, if we can write a hierarchy whose art level corresponds to the following relaxation. We are again asking minimize f of q subject to Q empty set is 1 and QS union T is positive definite, where S is an subset of size at most R. T is a subset of size at most R. And now this yields n to the n to the O of R variables. And this was first given by Lasher. And also we can, for example, I would like to point out one other thing. Suppose we, instead of looking at the moments, we can, since we are now dealing with convex problems, we can look at the duals. And in that case, for example, the dual of this moment problem corresponds to basically polynomials which are of the form the dual corresponds to polynomials P which are of the form Pj squared, sum of squares type polynomials. And since using the duality relation, we can basically ask this problem in the form of its dual, which involves now maximizing some beta such that the P is at least basically we can ask the related question. Yeah, P, yeah. Sorry. So basically we are now asking whether if there is a sum of squares type polynomial P such that if we sum Fn, such that if we subtract P from F, it is basically a constant polynomial beta. And this is again actually an SDP problem. And basically,
you didn't relax it. It's just this is when you look at
yeah. But basically, we can also relax it in the same way by constraining our attention only to polynomials of, by constraining our attention to only to polynomials P, which are basically degree at most degree D polynomials, degree R polynomials. And the nice thing is, yeah, but the thing is, we don't have to, because you know, if it is higher degree, this will be infeasible. So therefore, you know, I mean, it will still be true. It will just be meaningless.
So, yeah, but also in most problems we encounter, it is
Yeah.
good problems.
Yeah.
Always make them to poor.
Yeah. Actually, that's yeah, very good point. So all the problems we will be, I will look at actually most of them like will have either degree 2 or 3, and so this is due to Grigoriev, and what was the Pablo Puero? Parillo, yeah.
The Grigoriev name is positive Stahlensatz.
Uh-huh.
I read like this, it's SOS.
Yeah.
And this system is the strongest system we know, right?
Yeah.
Better than Loba's driver
And Shirley Adams. Yeah, so for example, yeah, okay, it's yeah. So so basically this is the strongest relaxation known, and for and I will talk about some other related hierarchies in the later in my talk, but so before 2000, for quite some time, even though we had very good integrality gaps for all, for any weaker hierarchy, we didn't know much about the sum of squares or Lacher SDP relaxations, and then the Grant Schönebeck showed that basically for most of the, for all, a lot of problems, basically the NP hardness of known NP hardness of approximation carries over to the these hierarchies. Yeah, but it's like really implicit there because it's Grigoriev only talks about linear satisfiability of equations.
The soft result is there.
Yeah, but you know, yeah, but so. Yeah, so
that they are not, so somehow there is gravity gap even if you go high in the iron.
I'm sorry.
That there are in gravity gap even if you go pretty high in the iron.
Yeah, but the nice, but the
For problems like Resat, so
yeah.
we need end around.
But the good news is that these the integrality gaps do not go beyond basically NP hardness. So, for example, for consider the problem of maximum cut. The best we know is 5/4, in terms of minimization version. So minimum uncut has NP hardness 5/4, and the best NP hardness, best integrality gap we know is again still 5/4 for these hierarchies, whereas when we look at the weaker hierarchies, it turns out it turns out there are integrality gaps which match the conjectured hardness. And just want to mention one exception. Except the problems which involve graph expansion, we have like integrality gaps matching UG hardness. But when we look at the graph expansion type problems, so only this is hardness.
So let me just integrality gap means that the program, the SDP, will deliver a solution that's much better.
Yeah, best possible.
Solution, unless you go.
Yeah, like you basically, yeah.
Exponential time.
Yeah, exactly. So, basically, if the optimum value of the problem is alpha, then these are such that the SDP optimum is at least some alpha plus, if optimum is all of these basically results have this property that any integral solution of the problem should have value at least alpha, whereas the SDP value is some epsilon times alpha. Basically, in order to certify that the optimum is really close to alpha instead of epsilon alpha, you have to run for a time of time exponentially in n, which defeats the purpose of the relaxation.
You mean if you want that SDP will be at least epsilon alpha?
I'm talking I will talk about minimization type problems.
Okay, but you wrote if the optimum is alpha.
Yeah, optimum can never be better than alpha, but basically.
The integrality gap is epsilon. It's one of them.
Yeah.
So if you want to achieve that the integrality gap will not be bigger than 1 over epsilon, then you have to go
to exponential time. Yeah.
Okay. So what is true except for expansion problems?
For weaker hierarchies, we have integrality gaps matching all known rounding algorithms. Let me put it this way. So for weaker hierarchies, for almost all problems except expansion type problems, some coloring except and a couple of other problems, we have integrality gaps which match the known rounding algorithms, and which happens to be basically matching the UG hardness. So, for example, for minimum uncut, right? We know that Sherali-Adams or actually even mixed hierarchies cannot get any better than what Gummins-Williamson will give you, and that's what I mean here. Whereas for the problem of say sparse cut, the best we know is 2 to the log n to the 1 over 6 or something like that. Whereas algorithm-wise, it's root log n. on the algorithmic side, Carlin, Matthew, and Nguyen showed that basically knapsack has like knapsack like for the problem of knapsack, the integrality gap matches dynamic programming.
Can you write a bit bigger for the
Yeah,
camera?
sure. When we are looking at when we are looking at if we are looking at 1 over epsilon rounds, then the integrality gap is basically at most an additive epsilon factor.
Although here it's very easy to get it without hierarchies, just by a direct algorithm.
Yeah, yeah. As Noga pointed out, we can easily get this with dynamic programming, but the problem is do these hierarchies have at least the expressibility power of dynamic programming? And then Klamtag, and then basically showed that one can get something like n to the 0.2 for 3 coloring. But the problem is, this is, for example, not so if you look at the problem of if you look at basically graph partitioning problems, then the best we know was due to Eden Klamtag, and then later due to someone else and Eden Klamtag. Who?
Some guys here were.
He was a student at Princeton, yeah, but I forgot his name.
I think it was with Sanjeev and Moses Charikar.
No, that's Eden. Yeah, but there was someone else. I forgot his name. But anyhow, the thing is, they showed basically improved algorithms for tree coloring, and also K coloring a three colorable graph, where K is something like this, and also coloring.
I mean, these guys improved it, right? Kawarayabashi and.
It's.
But they were using the same, so they have another combinatorial trick, but inside the same scheme, I think, that Klamtag.
I'm sorry.
So there is probably formally the best estimate is in a paper by Mikkel Thorap and this guy Kawarayabashi.
I see.
But this was using what Klamtag and his friends were doing, but they incorporated in it another combinatorial algorithm.
I see. I wasn't aware of that. Thanks. The thing is, these only use basically fixed number of fixed level of hierarchy, and so then with Venkat. in two parallel papers, we showed that many 2 CSP type problems can be solved using hierarchies, provided that they have a good they have a good spectral profile. And then, for example, Raghavendra and Tan using like.
Here you mean spectral because the 2CSP is a graph. So
yeah.
2CSP is a graph, you look at its spectrum, and if you know enough about the high rise.
Yeah, how fast they rise, then yeah. But since I'm like going to talk in more detail, right now I chose to just quickly skip. And yeah, Raghavendra and Tan for basically using building on the these ideas. They showed, for example, max bisection can be like they basically beat the Gummans-Williamson for max bisection. This was subsequently improved by but I will just mention this one. And then, for example, Aurora G. Partial tree coloring. And in fact, in a very recent work, Yuichi Yoshida and Yuan Zhao showed that one can get actually all the known additive factor approximation schemes for dense CSP problems using hierarchies. Basically, so and yeah, yeah, but the thing is, yeah, but the thing is, the idea, basically, the overall idea is still the same, and in fact, yeah, actually, if you use, yeah, like if you use stronger hierarchies, then number of required rounds drops by a log factor. But so now I will, in the rest of my talk, I will talk about.
So this what they can get for every dense.
For every k CSP problems on dense graphs, and also k like ordering problems, where you know you have ordering constraints on k variables, and you want to specify as many of them as possible. And also, if you can add like bisection type constraints, and like you know we like although we knew.
So it's still a bit weaker in the sense that we know algorithms in fixed polynomial, right? And they
Yeah.
the time here will be high degree polynomial if you want epsilon approximation.
Yeah. So. Yeah, here the running time is yeah, n to the 1 over epsilon. But the thing is, first of all, you know, the proof is like unified proof. They gave a unified proof. Like, if I'm not mistaken, like proofs of such algorithms were all over the place, and some of them were in fact quite complicated.
Yeah, no guy is only pointing out that in some of these cases we can get an epsilon approximation for any epsilon in n cube time.
Yeah.
Oh,
Oh.
for dense CSP, like in our
Yeah.
It's fixed polynomial for any epsilon.
But
for any dense CSP.
yeah, but
And I think that's the same. So things that use, at least formally, things that use regularity lemma or whatever, they are all
yeah,
fixed
I
polynomial.
think the point of this list is
just
just
to show
exploring
that
the
it
power
works,
of
right.
this
Yeah.
hierarchy to show that it captures, or maybe not completely efficiently, but lots of the techniques that were.
Right, yeah. Because
And-
it means that those, so this example is sort of like the knapsack thing in the sense that
yeah,
it gives
precisely, yeah, precisely, yeah,
it
yeah.
gives
It's something, at least, you know, like if you don't want to use big hammers, something you can also teach in a class in one lecture, right? Whereas, like, if you want to go all to the like all depths of like De La Vega or like earlier Aurora et al. Kind of algorithms, like they are kind of they are harder in the sense that like. But you are right. I mean, if you if one were like trying to like solve these problems in real life, this is like just like proof of concept. It cannot be used for anything else.
Question?
Yeah.
Are there any problems where, say, you have an empty task for all, or you know, you can do all epsilon, you know, in n cubed time, f of epsilon times n cubed, but the let's say the Serre hierarchy provably requires like n to the 1 of
No, none that I know. That actually that would be quite like I mean that would also be quite nice because like set truth is we don't know any integrality gap beyond NP hardness results. So like and that basically.
So it could be that if you go to the fourth hierarchy or something,
Fourth
fourth level,
Yeah.
then you get any epsilon.
Yeah, yeah. For all we know, yeah, yeah. We don't have any. I'm sorry. Yeah, we don't know how. Like we cannot rule it out, and such a result will, yeah, be.
Although knapsack is probably a good example.
In what sense?
Prove such an integrality
Ah,
gap.
yeah.
Probably knapsack can.
But it's yeah, like the integrality gap is only for like the weaker relaxations on knapsack.
I know. I'm just saying it will be interesting. So it seems that Lasserre with 4 rounds can do everything.
Oh yeah.
But you know, so the interesting things you suggest to prove would be to prove that it cannot do some pitas, and pitas which probably it cannot do. I don't know. I mean, but the conjecture would be it cannot do a pitas for knapsack.
Yeah.
In any constant, any fixed constant number of rounds.
So by the way, yeah, I apologize. I completely forgot to mention. So also, yeah, in a very recent paper also, Raghu and Avi also showed actually, yeah, integrality gaps for clique. And actually, I'm mistaken because this is better than NP hardness, right?
No, this is hidden.
Oh, yeah, yeah, yeah. Okay, yeah. Or,
Yeah, the main point is that it's average case, because if you just want click lower bounds for Lasserre, you can do just reductions. So there is a paper of Madhu Tulsiani which does reductions. He shows that yeah, so you can get integrality gaps for Lasserre from using you know already three stuff.
on any gadget
So
type
gadget
reduction,
reduction.
yeah, you can just.
Gadget reduction. So you can prove, for example, that click in the worst case, not the in the worst case, you know, there is an integrality gap if you do 2 to the square root again rounds. And the way you get it is by reduction. And this 2 to the square root again is what the blow up in the reduction. So you can do reduction. This is the average case.
Yeah. But yeah, still, this is actually, I stand by my point. This is because we don't know any NP hardness for that problem either. So this is, yeah, like I was wrong. I apologize. Yeah, there was one instance where we know integrity gap better than non-NP hardness. Yeah. Yeah. So now I'll talk about the rounding algorithms. Now I will look at the basically I will only look at problems involving like constraint satisfaction on graphs. Actually, just suppose let's say we are looking at the like unique games type problems. And I will write another formulation for the SDP, which then I will show is in fact equivalent to the original one. So since we can model any by lifting the graph, we can model any problem on with unique games type constraints as a problem on like cutting like is a problem of graph cut. We can basically I will look at this problem. So suppose we are trying to minimize given some weights. Actually, yeah, let's even forget about weights. So given a graph, we are trying to like minimize the number of edges cut subject to say suppose, yeah, we are looking at the problem of balance separator. It will be something like this, but or actually, yeah, to like look at the if we had some labeling type problem. So suppose we were given a unique games problem, which involves basically where for each edge actually yeah, I'm sorry, yeah, I think, yeah, this will be too much digression. So yeah, let's just look at so yeah, let's just look at the minimum uncut problem. So we are looking at yeah, I'll write them in a minute. So suppose we are trying to minimize over all edges. We are trying to find the labeling of nodes by 0 or 1, such that we are trying to make sure that we are trying to cut all the edges that goes between different labels, and we don't want any different labels assigned to the same node. So yeah, basically the problem of minimum uncut. And one, so how can we express this as an SDP? Well, and by the way, I'm assuming the edges are like appear in both, like edges are directed in the sense that for each edge between you and me, there are actually two edges from U to V and from V to U.
Something here. Do you want that it will be balanced cut or something? Or because otherwise the minimum is always 0, right? You could give all of them.
Yeah, thanks for, sorry, thanks, so basically we want to like assign at least one, like we want,
You can assign each of them label
0, precisely, so this condition, like which I forgot to write in the first place.
But where do you insist that half of them are 0 and half?
Oh no, this is just minimum uncut.
Minimum, but I can give all of them label 0.
It will violate this constraint. So basically,
you are subtracting in the objective function, you are subtracting the 0 label from the 1 label.
so now let's consider this. Let's consider this relaxation. Or what? Basically, let's say we replaced each of these indicator variables with a vector indicator supposed to be the indicator vector, and then what we have is basically u is equal to 0. So the dot product of same vectors corresponding same labeling should be 0, and then we will have basically first we will have a vector corresponding to the empty set, which is supposed to be the all ones constant function, and then so these two constraints correspond to these two constraints. And what about the moment type constraints? Well, now I will basically assume that we are trying to find like for every subset of size R, and now I'm trying to come up with an indicator I'm introducing an indicator variable for all labelings of subset S. For all such f. I want to now introduce a vector x sub s of f, which is supposedly 1 if all the variables in S are assigned, like are labeled with respect to f. And you know, if we were looking at the basically, if we were looking at the like in the in binary world, this the indicator variable for this will correspond to the following. So for all I in S, x so for all u in S, xu of fu. So basically, this is like the moment of basically, this is just the moment corresponding to f, and and now what I can write is basically and now I want to express the consistency constraint. First of all, suppose f and g were consistent, then
consistent that the variables that they share
Yeah.
give the same value also.
In the sense that f restricted to S intersection with T is equal to G intersection with G, or restricted to S intersection with T.
Do you want that it should
Then
be the S union T?
And here f.
Which function?
So which function should I use, right? So I should use like
Okay, yeah. So
yeah. Whichever contains U, like but and the square implicitly takes care of the 0, 1 nature of the problem, and then if they are inconsistent, it should be 0, right? Which also means I don't need this constraint anymore. And by the way, just in case you wonder how one can, whether if the like the second constraint, the vector vector equality constraint is SDP or not, just think about it as the distance, basically xu0 plus xu1 minus x0 all squared is equal to 0, which can then be written as an SDP constraint. Now, having defined that formulation, let me quickly mention that, for example, the problem of Sherali-Adams corresponds to the same formulation, except we require this x sub s of f and t, x sub t of g, that inner product to be only defined on basically s. So basically, this in case of in case of Sherali-Adams, yeah. So Sherali-Adams T is supposed to be a subset of S, yeah. Just like for the people who are familiar with Sherali-Adams, I wanted to point out, I'd like to point out this. So, yeah. And now, what's the nice property of this relaxation is that they allow us to condition.
So this is equivalent to the Lasserre.
I'm sorry?
This formulation is a sort of Lasserre formulation of the problem of mean uncut.
This is this is this is the formulation. There was one additional thing that we could have done. I guess you are referring to that.
No, no.
Okay, you are not referring to lifting the objective. Okay, yeah. Then this is
But just to make it explicit, you want the SDP constraint for this case. You just write down all the subsets, and for each subset, all the possible f's.
yes, yes. But the thing is, okay. So it's all. So one other thing is these. I can actually using inclusion and exclusion. I can write x sub s of f as just sums of its like moments of its subsets, right? And which means therefore basically. I don't need to explicitly solve this. I can still solve the relaxation and then just recover vectors x sub s of f by using inclusion exclusion.
Sorry, so what would be the variables?
You will kind of look only at f's that get only values 1.
Yes,
Right?
yes, yeah.
On subsets of the
F that get only value 1.
Yeah. So basically, I can get a.
But you will change. So the objective function will also use 1 minus.
Yeah, you just substitute. But the
so if you use this inclusion exclusion, we are back to the original formula.
yes, yes.
Where you have only variables for the subsets.
Yeah, exactly.
Like before, and the SDP condition
It's just PS-Stevens condition. Yeah.
I guess the SDP condition is on the matrix. In S and T, you have X, S union.
Yeah, yeah. No F's, no G's. Yeah. So so the nice property of such relaxation is the following. Basically, we can condition on events, in the sense that suppose we are given some F, okay, and then we want to condition on the event that all the variables in S are labeled with respect to F. So, in other words, I want to I want to condition on F, which means I want to I want to find these vectors which are still feasible solutions for n minus size of s many r minus size of s many rounds. So let me make it more explicit, then it will be clear. So let's just define these vectors x t condition on f g. Basically, this will say that x t union s f g. So now let's just consider these vectors. Oh, by the way, this conditioning was first observed by Lowash and Scriver for the Lowash-Scriver hierarchy. And it's something that is true for all these hierarchies. And but of course, in when we are not talking about SDP, this conditioning step is not so. I mean, it's not that there is no concise description. So what do these vectors satisfy, right?
So they are for all t's of size at most r minus s.
Yeah, but yeah. So I'm actually going to just assume that, if this is not defined, then it will be 0, so that, yeah, but this only makes sense for subsets of size at most r minus s. For example, what's the length of now? If we were, we conditioned on f, what's the length of this vector now? This is 1, right? So, yeah, this is this is basically the empty set on f, and we can just since this is s, and f this ends up being equal to the x sub s of f, and this is a unit vector now. Therefore, the length is 1. Moreover, if we now look at this inner product between G and H, still it satisfies all these required properties. Basically, it's consistent and zero otherwise. And most important of all is that it also has the marginalization property. In the sense that if I for fixed S, if I sum over all labelings, and then if I look at this value now, so basically, let's say this is a probability distribution. Oh, yeah, I forgot. Yeah. So this is if I'm sampling a label f with probability equal to the squared length of the corresponding vector, and now I'm looking at basically say x have a condition on f g. This is equal to and yeah, I forgot to mention for example, using this yeah, in this case for using these constraints, we can see that for any fixed S, if we just sum these vectors, they add up to x phi. And this is something that we don't have to explicitly enforce. It's implied by the previous two constraints. And so therefore, since these vectors are orthogonal, this means their squared lengths sum up to 1. Therefore, they define a probability distribution over labelings of S. And if and this condition says that if I sample a labeling from that distribution, and I look at the conditional, if I look at the conditional expectation, then it matches the expectation.
Looks like a probability distribution if we don't look at large sets.
Yes.
Including this condition.
Yeah. Yeah. Basically, yeah, it satisfies all the properties like of a proper probability distribution. It has like inner product corresponds to joint probabilities. The last condition corresponds to marginalization. But as long as we just restrict ourselves into small subsets, we can perform any operation which will be true for like a probability distribution. Now, actually, also I will let me denote this as the expectation where f is chosen with probability its squared length. So let me now use this notation where f tilde means like I sample f with probability.
So it's clear that f is on S.
Yeah. So now, basically, this also suggests a very simple way for rounding, right? Fix fix S, then sample F, and then basically use these conditional probabilities to round. And first I will, first let's analyze the third step, which will point out what kind of properties we need for such S, for S to be useful. And in fact, since basically we are now looking at, so this is basically like a zero, we can we can think of this as a vector y, which is just like yu of I is like some value between 0 and 1.
These U's are specific elements. They are not subsets anymore, right?
Which ones?
Yeah, so it's U. I mean, I'm just saying you use U, X U sub F, right?
Yeah.
So U are now individual elements.
Yeah.
They are not sets.
Yeah.
You're now giving the Boolean values to the original variables.
Yes, you are, yeah. U's are now singletons, yeah. And yeah, so I have basically I can think of YUs as basically the solution of an LP relaxation, right? And how at this point, suppose furthermore, size of S was equal to R. This means I'm stuck here. I cannot go any further. Therefore, I have to basically, all I can do is really look at these values. And let's say, what's one simple, okay, so yeah. And let's look at the following, right? We want y's to be as close to an integral variable as possible. So we want them to be close to 0 or 1. How can we measure this? We can just look at basically the sum of their variances. If I think of yu as a random variable, I can basically just look at this now. Summation over all u. Like I can for each u, I can look at this now. Like sum y sub u I 1 minus y sub u of I, right? So I'm just looking at this a simple polynomial. No, I cannot, right? Because this is concave now. And if this is this is good if it is something small. So I'm like basically trying to minimize a concave function. But the thing is, now the question is like, does there exist some S and some F such that this value is small? And
the S is used somehow to correlate all the values, right? I mean,
yeah.
We have some solution to the SDP.
Yeah.
And we try to round it, and we use some small subset S to correlate all the values.
Yes, yes. And the thing is, yeah, we don't want to, yeah, like we cannot. This is not like FPT where we can fix S just by looking at the input instance, because then SDP can cheat. Therefore, all we can, we want to choose S by looking at the vectors themselves. By without, we have to choose S without looking at the input instance. We have to look at the SDP instance. But anyhow, so for example, here is one thing. At this point, suppose we use the simplest possible thing for each u. Choose I with probability right? And in this case, for example, if I were to do this, I just want to show how this will arise in this context. If I were to do such a independent rounding, so this will be independent because I'm choosing all u's independent of each other.
There was no S. No, there wasn't. I mean, you got Y from some F.
Yeah, but now at this point, after I fixed F, for each variable, I'm choosing it independently at random. The thing is, for variables in S, even though I'm doing it independently, they will still correlate properly with f. I mean, they will still receive f because at those points, I made sure that my solution was integral.
So can we think, for example, just to make sure the intuition is right, so can we think of the Gomans-Williamson algorithm as one in which the S will actually define the hyperplane, and then Y will already be Boolean?
No.
No.
No, we cannot.
No, it's not.
Yeah, unfortunately, that's, yeah. Like, you can think of Gomans-Williamson as, you know, actually the following, and this is how Raghavendra-Tan works. You fix f, and then you do Gomans-Williamson on these vectors. XU condition on f. Like actually a function of those vectors, but
You do the Gomans-Williamson rounding on this.
yes, yes.
But the length should matter, no? I mean,
Yes,
Gomans-Williamson, they're all unit vectors.
yeah. So that's, yeah, you have,
You have to do.
yeah, you have to do like a couple of more tweaks, but like in a minute it will be clear actually what kind of vectors that needs to be used. So I don't, yeah, right now. But here, for example, yeah, just let me point out for all v in S, y v of I is equal to f of v actually. Sorry. So even though, for example, so this is this is one if f of v was equal to I and 0 otherwise. So even though I was here doing random, if I were to do independent rounding, y v's will all the variables in S will receive the correct label. Okay. So, and you know, what's the now with respect to this independent rounding? What's the probability that h u v is cut? Right. So this is so this is like so after this labeling. And so this will be equal to so this quantity here will be bounded by 2 times the variance of so this quantity will be bounded by 2 times the variance of plus the variance of right. So and here I also use the fact that yu0 yu1 is sums up to 1, right? So basically, I mean, this is just after some basic algebra, I can bound the probability of an h probability that an edge will be left uncut with this quantity here. So this means now like the total number of uncut edges I'll have. Just one more thing. So plus so basically like the probability that an edge will be uncut is SDP value plus 2 times the variance.
But the SDP value doesn't have to every edge, it has just a global.
Yeah, but so here I'm using this in in this form. So basically 0 xv f1 squared plus the other way around. This is what I mean by SDP value. So, but the way to think about this is, you know, this is like so SDP gives me a probability distribution on the event of cutting an edge, right? I have these and I have now these probability distributions y sub u's, and now I'm measuring how close this probability measure is to the one given by SDP. And since I'm like rounding each node independent of each other, this means this distance probability, like distance in probability measures, is upper bounded by the variance, because yu and yv are like chosen independently at random. And basically, and this is how I get this term. And this is, yeah, basically, yeah, if I measure the distance between, yeah. So I'm measuring like the probability distance, the total variation distance between like the event between, yeah, like this independent rounding and the SDP value itself. And it turns out it's equal to this value. But then what's this value? And yes. Yeah, but since I don't know, I have to basically I mean, since this graph might not have a small independent set, I have to basically do all independent round all of them independently of each other. I cannot get away with just pairwise independence.
No, isn't this calculation?
Oh yeah, 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 yeah. Two comes from like the first you apply Cauchy-Schwarz and then use arithmetic geometric mean. But the thing is, like actually you can like there is a like there is a like there is an equality like identity based statement, which I mean there is also a stronger statement, but I will come to that at the last part. Right now, so and our question now becomes what's y sub u of I, and also since we are only looking at like labelings of one, let me drop I and just look at yu, which is defined to be y sub u of 1, and so basically we are interested in this quantity, expectation over f x u of f 1 minus we are interested in this quantity, right? So see, first part, because of the property of expectation, like conditional expectation, this is equal to the first one here, like will be equal to, after taking the expectation, will be equal to the xu1 squared. And the second one will be, let's just write it algebraically. So x u of f to the 4th power times right. And now, I'm sorry? And the probability that I pick f. F, I'm sorry, yeah. And now here, what is this? This can be written as the, like, empty set of like condition on F, right? And remember, since we are dealing with, we are only looking at binary variables, like our constraint, if you remember the consistency constraint, this quantity here is equal to the squared length of this vector, and this means the fourth power is equal to the squared length of this quantity. And now, this is equal to basically x of f, x of, by just substituting everything. This is xf to the fourth power. So this quantity here, right? So let me use this here. I'm looking at this quantity here, right? So by just like I is 1, yeah, but like in the general case. So here I'm looking at this quantity, and what's this vector? Like by the definition of conditional vectors, this is equal to x of f divided by length of f, right? This corresponds to this vector. Here, this is basically x of u and f, it will be basically, yeah, like x. This will be this vector, and because of the denominator, I will get another x of f length, and here, this quantity is equal to basically, here I am conditioning on, like I'm looking at probability of u receiving 1 and f happening, and looking at the inner product of this, and I'm looking at probability of f happening and u receiving 1 and f happening again. And because of this joint probability property, this will be equal to just x of f, x u of 1. And now I can write this as minus f Yeah, so these two, this one and this one will cancel. Denominator will be squared. Now, then it means I'm basically measuring the inner product of xu1 with the unit vector along the direction of x of f. So yeah, basically, now if I define this vector, this matrix pi sub s as the outer product of the normalized vectors for each x of f, then that quantity this quantity can be written as xu minus pi of s right, just doing some linear algebraic substitution. Yeah, because here this is equal to, I mean, I can write it as xu transpose xf, other product f xf times xu, and I can push the summation over f inside, and then I can define the matrix inside as pi of s. Okay, and the most important thing is, remember, x of f's each correspond to, are inconsistent with each other, and they are unit vectors. Therefore, this is a projection matrix. Which means this quantity is now equal to pi of s perp xu1, where pi of s, where I can now define pi s perp as the projection matrix onto the null space, or onto the orthogonal complement of so if I look at the span of these vectors x sub s of f, and if I look at their orthogonal complement, pi of s perp is actually just a projection matrix onto that orthogonal complement.
What do we expect to get its n? So you're trying to estimate surrounding. Right?
Yeah. So the problem is, we want to get rid of these x of f vectors. We want to get rid of them because they are very hard to reason about.
Okay.
So we want to get rid of them, and we want to basically obtain an expression which only involves x of u type vectors. That's our goal.
But you will have to fix S or to choose S somehow, right?
Yeah, but when after I relate, that will give me an idea on how to choose S.
Okay.
Right, so now, oh, okay, yeah, I can, yeah, so. But really, the crux of the argument is that pi sub s is actually a projection matrix, because the fourth power, if there were no way to cancel out this fourth power, we would have been in trouble, because we cannot reason about such rational functions. But when it cancels, we have a nice object which we can reason about. And now just let's look at one property. Say we take any vector v in S, and let's calculate this product here, right? What will this be? So this will be basically all f, where f of v is equal to no, not perp, just projection.
Oh, the projection.
Yeah, but you are spoiling the ending. So I'm summing over all such f's, and again, by marginalization property, this should be equal to basically vi itself. Therefore, this is equal to 0, which means now this matrix dominates in PSD ordering the matrix which is like the matrix obtained by projection onto the span of so this means and if I can denote this matrix as P of S.
And this is for both I
Yeah. But in the end, I will just fix I to be 1. So if I denote this matrix by P of S, where now P of S is a matrix only defined using these first order vectors, which is what I wanted all along. For all variables, let's just form this capital X matrix whose columns are XU1. Then finally, expectation over F of finally now I can upper bound this sum of variances as I'm taking like the minor of I'm looking taking the columns of X corresponding to S. I'm looking at the projection matrix onto their orthogonal complement, and then I'm multiplying the matrix X with this matrix. So I take each column of X, each XU. I project it onto the orthogonal complement of the span of vectors in S, X U1 in where U is in S. Yes. Yeah. Yeah. PS is excess. PS is excess. I mean, so identity minus PS is excess perp. Okay, yeah, so now, and this is Frobenius norm, but this just means, like I'm looking at the squared length of each column of X, each column of this matrix. And since this is projection matrix, like it's symmetric and its second power is equal to its first power. Okay, so now basically the rounding gets a solution of value at most now 2 times so basically now after rounding the solution I get, how much its value is larger than the SDP optimum is upper bounded by this quantity here. So this question is now I'm trying to choose R columns of X so as to minimize right, and then how small this quantity can be? Well, if I were not restricted to choosing columns of X, I could, if I were able to choose any rank R matrix, then this will be at least the sum of smallest n minus R eigenvalues of X. Right, and then basically with Venkat we showed that you can choose say if R was something like K over epsilon, there you can find a subset of size R such that there always exists a subset of size R for which this quantity is at most 1 plus epsilon times so basically if in the for example
Sorry, what is the bound on the R?
R is K over
by
K over epsilon.
yeah
There's
so
something above the K
which is supposed to be erased, but basically if you can choose like O of R columns such that the this quantity is very close to like best possible rank R error, reconstruction error, and
statement about what do you assume about this statement about matrices in general?
this is any given a matrix, so you can always find like O of R columns such that the error is like close to you can do it like you can find R columns which do as good as SVD. And finally, now we are basically so our basically our rounding error is just this quantity. Now we are looking at the.
you can look only at the SVD.
I'm sorry.
You look at the SVD
Yeah.
solution.
So
you
we-
related it to the SVD.
Yeah, we got rid of x of f's. We got rid of the vectors in S. We got rid of S. And finally, we are left with only the spectrum of X itself. So basically now we are trying to answer this question. How large can this quantity be given that given that if I write the objective function as the Laplacian matrix, given that the trace of that Laplacian times this matrix, the inner product of the trace of Laplacian times the gram matrix for X is equal is at most SDP optimum.
So this trace is just a objective function of the.
Yeah, so this is supposed to be like this thing here. But the thing is, here then I can do like one more transformation to write this as xb of 1. So basically, L is the now lifted matrix, right? Okay, so I'm looking at this. So basically, what I know is this inner product is something very small, right? And then I'm wondering how large can the smallest n minus r eigenvalues of the of this X matrix can be.
So this should be related to the top eigenvalues of the Laplacian.
Yes. So here, this is I can use just von Neumann's trace inequality to say that this is lower bounded by jth smallest eigenvalue of the Laplacian times jth largest eigenvalue of this matrix X. Since both of these quantities are positive, this is at most, and lambdas are in increasing order. Basically, lambda r is smaller than lambda I, where I is larger than r. Therefore, and this means now this quantity here is upper bounded by SDP optimum divided by the art eigenvalue, which means, and here, yeah, give me one. Yeah. So which like if I assume the matrix here I'm assuming the matrix is normalized, by the way. So these eigenvalues are all between zeros and twos. Therefore, if like for R, like if the art eigenvalue is constant, this means like we get the constant factor approximation for minimum uncut problem. And yeah, this concludes the thing. And in last 2 minutes, I want to quickly mention the other generalizations. About any questions so far?
So the big thing is that still lambda r will be very close to 0.
That's the very bad thing, yeah.
That's not the bad thing.
Right, so
Yeah.
Without the bad stuff.
But yeah, the question is, yeah, like how fast does it become like
if it has only a small number of
yeah.
pieces that are separated, and besides that it is an expander, then
Yeah, like if it is like a nice small set expander. And yeah, actually this gives, for example, an alternative proof of also the sub-exponential time UG algorithm from ABS, because what they have is, if lambda r is small, then they find like lots of loosely connected pieces, which then you can recurse on. If lambda r is large, then you can just round it using this algorithm. So this gives like basically an alternative proof for ABS.
so you don't. So you save this exhaustive search on.
Yes. Yeah. So
Exhaustive cells on the space of
span of
no, it's different.
yeah.
Probably, I don't think.
The running time is still.
The running time is the same.
So I want to mention, for example, this was like in a work of Aram Haro and like Aram Haro et al. In stock 2013, they like basically used like such a rounding scheme for like quantum for quantum computations. They proved I forgot the name of the theorem, but like they like basically use this to find like round the correlated state of a quantum computation. And so this is not like restricted to 0 ones. And then for like for non-uniform sparse cut or such problems, lambda r dependence will be terrible there, because lambda r in such problem you don't expect lambda r to be large at all. But in that case, by just tweaking the rounding, like you can get like 1 minus factor approximation, and all like for the problem of tree coloring, Sanjeev and Rong, they again used a slightly different way of like rounding instead of independent rounding to get to show that if the like top art eigenvalue of Laplacian was smaller than something like some fixed constant, then you get a like basically omega and partial coloring, which means you can get like n over 12 size independent set. And then basically using the using the small set expander framework I talked about last week, one can also replace lambda r here with like art small set expansion.
So the result from the coloring is that you can color by log n colors.
No, you want to find a partial coloring with 3 colors.
And then you cannot repeat it.
You cannot. You want to like say that you want to color as many nodes as possible.
Right.
Yeah, with 3 colors, and they show that you can color like something like n over 2 many.
But you were saying that they cannot repeat it because
But wait a minute, they find this independent set under this condition.
Yes.
Yeah, but then this condition will not hold for the subgraph.
The thing is, yeah, it's like because you are looking at minor of a graph. I mean, it's not a minor anymore. Induced subgraph, yeah. But the problem is, since it's not minor, like this condition, even though it held for the larger graph, it might not hold for the smaller graph. But
Should we expect this condition?
Yeah, I don't know what is this condition that it's not.
Yeah,
So
I guess it, yeah, so yeah, it's actually a weak condition. So almost all the eigenvalues.
And we want R here. What do you want R here?
R is, let's say, constant, yeah.
so, but your running time is n to the r, so you can choose R to be.
Polynomial algorithm, so you want R to
Yeah.
be constant.
And actually, let me mention one more thing. All such algorithms, like we showed that also in another paper with Venkat, you can implement them in time 2 to the r. So in this case, if you are like in this case, you can assume r is log n. And this is again for normalized Laplacian matrix. Therefore, it's like it starts from 2 and decreases gradually. So yeah, and like at what point does it become like yeah? And you know, since for these problems we know nothing, actually the range of r people think about is like n to the epsilon. So we are trying to rule out or like see what happens for sub-exponential time.
But again, so this is some sort of assumption that the graph does not have too many eigenvalues that are close to the top.
Yes. Yeah.
So it's sort of an expander beside some small pieces.
No, it's the opposite. No.
It's opposite.
It's really a very weak condition, I think. No?
I don't know, because I actually, to be honest, I don't have much intuition for what the top spectrum looks like. Because you know, lambda n measures like how close it's to bipartite graph. But then, like when it decreases, yeah, like.
Tells you sort of how close it is to our correlative graph.
I see. Yeah. Actually, yeah.
Because it's,
That makes perfect sense. Yeah. But I guess there is nothing formal as in the sense of like small set expansion for the this regime, right? Yeah. But yeah, this concludes my talk. So thanks for listening. Any other questions?